Greetings and welcome to Distillate. So, in today's lecture, we are going to discuss implicit ODE solvers. Okay, so implicit solvers are important because for certain ordinary differential equations, what happens is that if you use explicit solvers, after a certain time step, they become unstable. So, you will get a solution that is very unstable in nature. Okay. Uh, and with implicit solvers, the solution is still stable at that particular time step. So when you use time steps in ordinary differential equation solvers, there needs to be a certain limit that it must be within for this to be stable. So for example, if delta t exceeds a certain limit for explicit solvers, you get unstable solutions. And similarly, it could exceed a certain limit for implicit solvers and it could become unstable. But when you do a proper stability analysis, you will see that the limit, or basically the range of delta t that you can have with implicit methods, is a lot more compared to the range of explicit methods. So for a number of or for a huge range of delta t, you get a stable solution with implicit methods. But with explicit methods, that range is very small. So at times you need to give really, really small time steps to get a stable solution using explicit methods. So although per iteration, explicit methods might be easier, but since the delta t or the time step that you're using, or maybe the length step or any step size that you're using is going to be so small that it would altogether take a lot of iterations, and that would just mess up your entire solution. So you really don't want to do that. And in such cases, you use implicit solvers. Okay. So let's start with simplest implicit solver, which is Euler's implicit method. So you already learned about Euler's explicit method in the numerical ODE videos. So today we are talking about Euler's implicit method. So it's very slightly different from the explicit method. So let's say you are solving for dy by dt is equal to some function of t comma y. So when you solve for this using the Euler's implicit method, what you will be doing is you will be saying that y at the next time step is going to be y at the current time step plus the time step times this f. Now with explicit solvers, it would depend on this time step itself. But with implicit solvers, it would depend on this time step. So it's going to be f of ti plus 1 comma yi plus 1. Okay. So because the prediction at the next step depends on the value of the next step itself, that's why this kind of solvers become implicit solvers. So any solver where you will see the RHS containing the time step that you're trying to predict itself, the value of the time step that you're trying to predict itself, that's an implicit solver, right? So this over here is an implicit solver. And over here, of course, yi is known because it's the value at the current step. Ti plus 1 is also known because Ti plus 1 is just a Ti plus delta t. So that is also known, right? And even your time step is decided by you. So this would also be known. So altogether, there is just one unknown. There's just one unknown. And that one unknown is yi plus 1. Okay. So all you need to solve for this one unknown is one equation, which is this equation over here, right? So one equation, one unknown, and that solves for your the prediction, right? So if we get everything to one side, we'll get yi plus 1 minus yi minus delta t times f ti plus 1 comma yi plus 1 equals to 0. And since yi plus 1 is the only unknown, you could finally just write this down as gyi plus 1 equals to 0, right? So all you need to do is solve this for yi plus 1, and that's it. That's all that you need to do for a certain iteration, a particular iteration, right? And we've all learned this function could be linear, this could be non-linear, and we've all learned how to solve for such functions using Python, and that is the use of fsolve, right? So in fsolve, you need to give the function itself, which is g over here, and you need to give an initial guess, right? So the initial guess that I usually use for implicit solvers is an explicit solution. Okay. So for example, if we want to predict yi plus 1 for the implicit solver, we would use yi plus 1 equals to yi plus delta t times fyi comma ti, right? So this is the explicit solution. So we'll use its explicit solution as the initial guess to predict the implicit solution. Okay, that is what I generally use. Another initial guess that you could use is yi itself. So that is another thing that you could use. So basically, there are you could get very creative with the initial guesses. So if there's something else that you use or you would like to use, please do mention that in the comments over here. But this is something that I use for my problems. Okay. Now there's one more thing that you need to tackle, and that is the fact that yi and ti plus 1 would also change with each iteration, right? yi and ti plus 1 could also change with each iteration. But you cannot really define g in your Python code with yi and ti plus 1 as additional variables or additional arguments. So as you remember, whenever you define a function, you have the function name and you have arguments, right? And then you return certain thing, so a certain value, right? So if you will do that for the function over here, you would have to define g, which would be a function of yi plus 1, but it is also a function of yi and delta t, even though they are constants, right? So it would be a function of yi and delta t, which are constants. And then what it would return is this thing, yi plus 1 minus yi minus delta t times f ti plus 1 yi plus 1, right? That is what it is going to return. But when you call this function in fsolve, right? When you say fsolve g comma some initial guess, it would actually end up using all three of them as variables. So it will try to give you a value for all three of them. But yi and delta t are fixed. Okay. So you really don't want to define them as arguments over here. Okay. You don't want this to happen, right? You just want there to be a single argument, which is yi plus 1. Okay. So what now we could do is we could define yi and delta t as global variables. So we can define them outside the function, right? We can define them outside the function in your while loop, right? In the while loop where you're calling this fsolve. So basically, before you call for fsolve, you define the variables yi and delta t and even ti plus 1 over here, and you define them as global variables. And after that, you call the function g. Okay, so therefore it will need just one argument because the other two variables in the function are coming directly from global variables. Okay, so we'll see how to use this in Python. When we'll write the code, it would be a lot easier for you to understand. Okay, so let's start by a simple equation where we are trying to predict, or we are trying to solve rather, dy by dt equals to minus 5. A very simple problem over here. Okay, And this also has an analytical solution. So for an initial guess of, initial condition of t equals to 0, y equals to y naught equals to, let's say, 1, right? This is going to have a very simple solution, which is y naught e to the power minus t, or e to the power minus t. That's all, right? Because y naught is 1. Right. So this is the analytical solution. So now we'll use both explicit and implicit Euler's method to see which one performs better. And we'll see for various time steps what exactly happens, whether where exactly does it start going unstable, and so on and so forth. Right. So through this, we'll also get an understanding of what I mean to say when I say that the solution becomes unstable. Okay. So let's go to Python and let's firstly define what should be the final time. So let's say we are going to compute all of this till 100 time steps. Okay. And let's say we will also have to give y naught, which is the initial guess, initial condition. And then let's get the analytical solution. So let's define time array, which is np dot line space start, stop, and let's say we want 1000 data points, and we could define a y array, which is just y naught e to the power minus time, right? So that is how you define y over here. That's the solution. And let's now plot this, right? So t array comma y array. And now we want a legend plot. So we want this to be labeled as analytical solution. So we will say label analytical. Okay. And if you want it to be a legend plot, and if you want a legend to be displayed, you can say plt.legend before plt.show. So that will give you a legend. So whatever color of the line has been used to plot these data points will be corresponding to analytical, the label analytical. So you will see over here, we have the blue line corresponding to the analytical label over here. Okay. So we have the analytical solution here. Now let's start by our implicit solver. So let's say implicit Euler's method. Right. So what we are going to do now is we are going to once again start with an initial time t array equals to 0, and we are going to start with an initial y array, which is going to be y naught. Okay, which is initially going to have y naught, and we will say that while the previous while the previous the last element of my time array is less than tf, it should keep on going, right? This thing should keep on going. So, and let's define dp. So a time step over here, which is 0.1. Okay. And yeah, now we are going to use implicit Euler's method. So let's first of all update our time array. So the previous time plus delta t, right? That's the time array updated. So remember, when you say t array minus 1, that is equivalent to saying ti. Okay. And similarly, y array minus 1 is equivalent to saying yi, right? So in your mathematical formulation of the Euler's implicit method, wherever we have yi, I'll be using yr minus 1, right, over there. So that's the idea over here. And now let's try to get the prediction, which is yi plus 1. So for that, we'll have to use fsolve. And before that, we'll have to define the function that we are going to give over here for fsolve. So let's say def g y new. Okay. So there's supposed to be just one argument, which is going to be yi plus 1, which I'm referring to as y new over here. Okay. And that is just y new minus y old, which is going to be globally defined, minus dt, which is again globally defined, times f of yi plus 1, comma ti plus 1. So f of yi plus 1, comma ti plus 1 in this case is just minus y, right? So this is just going to be minus y new, right? That is all that I've done. Okay. And let's return that. So in this, y old and dt are globally defined. Dt has already been defined here. Let's define y new. So sorry, y old. So y old is just yi. So that's all, right? And now let's say scipy dot optimize f solve the function name, which is g, comma initial guess, which I told you is going to be yi plus dt times fyi, which is minus. Right? So this is the explicit solution that becomes the initial guess. Okay. Now fsolve, what it returns is the array of variables such that the function returns 0, right? So it gives you an array. The result from fsolve is in the form of an array. So since there is just one variable over here, it will just give an array with one element. So we have to extract that one element, which we are going to extract like this. And we are going to append that in the y array. Okay. So that is what we do. We append our solution from fsolve to our y array. And that is it. We have been able to solve this. So let's now plot. So plt dot plot t array comma y array, and this will be labeled as implicit solver. Okay, this would be labeled as implicit solver. So we see they are following each other very closely, both analytical solution and the implicit solver. Now let's compare it to explicit solver over here. So we'll not redefine dt, but we'll copy everything down first. So explicit solver has a very similar code. So explicit Euler's method has a very similar code. So let's not define this dt again, right? T array is again going to start with 0, y array is again going to start with y naught. And all that we are going to change is we are going to remove y old because that's not needed anymore. And this thing is going to be appended, right? This thing is going to be appended. So I'll remove everything else and just append the explicit solution, right? That is all that you have to do. And this is an explicit solution, right? So if we plot the three together now, we'll see that they are following each other very closely, right? Let's try to reduce the time, the final time, just to be able to visualize this thing a bit better. So if we then run this thing, we see that all of them are following each other very closely, right? Now let's try to play with the time step to see how each solver behaves, whether the explicit one is better or the implicit one is better. So let's make it 0.5. And now we see explicit has gone lower while implicit has gone slightly higher. Let's go on and increase it further to 1. And now you see the explicit solver is really doing a bad job compared to an implicit solver. It is not even able to get the shape as properly. Even if we increase, let's say the time, the final time to, let's say 20, the explicit solver does a really bad job. Okay. Let's further increase the time step to, let's say 2. And now you see explicit solver has become unstable. Okay. So this kind of a solution, this over here, is what I refer to as unstable. So now you see at a time step of 2 itself, so just to begin, at a time step of 1 itself, it was not performing very well. But at a time step of 2, it has become unstable. Now let's say I had to solve this equation for, let's say, 1000 seconds. So I would have to take a time step lower than 1, and it would take a lot of iterations. But with implicit solvers, I could go even higher. I could, let's say, take time step of 5, and I would see that the explicit solver just becomes very unstable. But if I just leave it out and just try to see if the implicit solver does some job, so it is still able to make some predictions. Not very good, but it is still able to do these predictions. We are still able to get some trend at least. So even at a time step as high as 5, implicit solvers are giving us good solution. Not very good solution, but it is giving us some trends. But with implicit solver, with explicit solver, it is just going unstable, right? So that is not something that we'll want. So this kind of an unstable solution is something that we try to avoid, right? In more complex cases where you are now not just solving ODEs, you also solve PDEs. So in such cases, the implicit solvers become even more important, because even for tiny time steps, explicit solvers become unstable, right? So you really need better implicit solvers in such cases to sort of get a stable solution. Okay. Now, before I end this lecture, I would also like to talk about multiple uh, ordinary differential equations, just like we did for uh, Euler's explicit method. So let's say we have a system of ODEs. So the system of ODEs can, let's say, be represented in this way: dy by dt equals to some vector function of y comma time, right? So this is basically let's shift this down. So over here, I'm talking about system of ODEs, right? So over here, this could be, let's say, dy1 by dt equals to something, dy2 by dt equals to something, and so on and so forth, right? Till dyn by dt equals to something, right? So we have n ODEs. So this becomes a system of ODEs, right? And this is how you represent this system in a compact form, right? In a vector form, right? Now, once again, all you need to do is you need to use our implicit method for this case. So we'll say that y at the next step is equal to y at the current step plus delta t times the function at the next step, comma, time at the next step, right? And once again, you bring everything to one side. Now this may look scary, right? This may look scary, but eventually, once again, we see that the entire vector yi is known. Okay. The entire, not entire, ti plus 1 is known, right? Delta t is also known or decided by us, so it's fixed, right? So all that is left is yi plus 1 vector, which is unknown, right? So yi plus 1 vector is unknown. So let's say there are n equations over here, n ODs over here. So we have n unknowns over here, right? But once again, this is a vector equation over here. So there are n such equations as well. Okay. So you have to solve this system of, I'll write with a white pen. So you have to solve this system of linear or non-linear, whatever it is, equations once again to get the vector yi plus 1. So we solve for this in order to get the vector yi plus 1, right? And that's it. Once again, you'll be able to do this using fsolve. So instead of getting a single value per iteration, you'll get n values per iteration. And that is all that you need, right? So we'll come back with a few more tutorials. We'll probably do some tutorials. I'll try to get some different ODEs, not the ones that we've already done, just so that we have a better idea of how to use implicit methods. And so that you're also exposed to some different ODEs that you might come across in chemical engineering. But basically, through tutorials, we'll learn how to use how to use implicit Euler's method for a system of ordinary differential equations. So with this, let's end today's lecture. Thank you.